I want to start off this lecture talking about something that maybe you've heard of before called spin. So electrons have a property called spin, and really that's a bit of a misnomer. It's not that electrons are spinning per se. The property of spin is really more to do with magnetism. So like magnetic fields, for example. We know this because if we were to take an electron and say, let's design some sort of a system where we've got a channel between two magnets. So suppose we've got a magnet on the top and a magnet at the bottom with some opposite poles. And if we were to fire our electron through the channel between these two magnets, we would find that if we fired, say, 1 billion electrons through this channel, 50% of them would be drawn upward toward one of the poles, and the other 50% would have been drawn downward. And so we've no choice but to gain from this experiment that electrons have a magnetic property to them. They are drawn to the poles of a magnet. And likewise, they have really only two options. They're either drawn up or they're drawn down. In other words, absolutely none ever go through the middle and are not drawn in any direction. So this just doesn't happen. Therefore, we say that electrons possess magnetism, and we essentially call that property spin. So maybe somewhat of an awkward name, but nonetheless, it is a real thing and it exists. And we need to take it into account if we're going to finish off our discussion of many, many electrons together in the same atom and trying to understand what orbitals are all those electrons in and how do all of these electrons coexist with one another. That's a challenging thought, I think. And spin is something that we absolutely have to take into account. And so that's what I want to do today. Electrons have spin, they have magnetism. And what I want to do is bring back a diagram that we've been working on over the last few lectures, so the energy level diagram, or an orbital energy level diagram, as we've been talking about. And what I'd like to do is I'd like to indicate in that diagram where my electrons are. So if I bring back this diagram from previous class, what I'd like to do is I'd like to describe my electron as being in one of these particular orbitals, one of these particular energy states. And so the way I'll do that is first by just getting rid of a lot of these pesky labels, because now that we know how to label these things, I no longer need them. And we'll leave the angular momentum quantum indicators there, the SP and the D. So I want to indicate that I've got electrons in these particular states. Generally how I do that is I draw a half arrow like that. Okay, so notice that's sort of a half arrow pointing up. And that is a symbolic indication of an electron, and I can place that half arrow, I can place that electron in the 1s if I want to do that. Or I can place that electron in the 2s if I want to do that. And that electron, not surprisingly, can be dragged really to any of these states I want to put it in. Okay, so this is how we indicate an electron being in a particular state in a diagram. Okay, so how do I incorporate spin? Well, because electrons come in two types, essentially. They come in two different magnetisms. They come as being able to be drawn up or being able to be drawn down. What we'll do is we'll introduce another symbol, which is essentially the opposite of the first, which is a down arrow. Okay, so this is going to indicate that I've got two electrons now, one of a particular spin and the other of the opposite spin. There's only two types, so let's use an arrow going in two different directions. So this is how I would indicate a particular pair of electrons. Not that I need to pair them. Of course, I could just take an electron and put it over there in that energy state if I want to, and I could take this electron and arbitrarily put it in that state if I want to. But the point is that I now have diagrammatic tools to indicate where my electrons are in this orbital energy level diagram. Okay, so this is important. Now, the second important piece of spin in terms of what it tells me, for reasons we won't go into in much depth in this particular class, but reasons that I think are reasonably intuitive anyway, because these electrons are essentially magnetic and they do have opposite spins, it's true that they tend to pair. It's true that they tend to come together in pairs. And so it would not be surprising at all, for example, to find two electrons both being described or both being in, per se, a particular orbital, say the 1s orbital in this particular diagram that I've got here. That is not only a reasonable thing, but it is something that is experimentally verifiable. So we can excite electrons, for example, and based on energy differences between states, you can more or less deduce that you had two electrons in a particular state. Using some analytics that I won't talk about. But you can do this. So you've got two electrons in a particular state. So that's useful information, because really what I would like to do today is I would like to complete this diagram with electrons to help me envision what many electron systems look like. So what about, something like carbon with 6 electrons? Where are all those 6 electrons? What are they doing? How can I visualize this in my mind? To understand how a carbon atom behaves. How can I understand how a carbon atom makes a bond if I don't really understand what its electrons are doing? And so really what I'd like to do today is put these electrons in the diagram, which is something we haven't done yet. So then I discover that I've got two different types of spin. Okay, that's great. And I can indicate that with an up half arrow or a down half arrow. And it seems as though I can put electrons together. I guess the final piece is, could I put 3? Am I allowed to do this, for example? Can I say that there's 3 electrons down there in that 1s orbital? And the answer to this question, very importantly, is no. And again, for reasons I'm not going into in a lot of detail, but this is not possible. We can't put 3 electrons in the same orbital. In fact, we can't even put 2 electrons in the same orbital if they are of the same spin. So I cannot do this either. And again, this is experimentally verifiable, and the intuitive explanation for this is just that these electrons are not only both negatively charged, let's not forget that, therefore there's always some repulsion between these electrons. They don't want to be close together necessarily, but they're also of the same spin. So we've got magnetism and electricity both working against us here. We've got same poles, same magnetism, if you will, operating to keep us apart, and we've got our electronic charge operating to keep us apart. This is an absolute no-no, and we don't see it. We don't have this. We don't have this option, really. Electrons will never do this, and this can be, again, experimentally verified. We can understand the spins of electrons in certain contexts, and we know that this doesn't happen. And so it seems as though we've got some rules, and these are rules that probably you would be familiar with from high school, but essentially what the rules say is that if we want to place electrons into orbitals, we can only place 2 electrons of opposite spin in any particular orbital at the same time. Now, you might be asking, that second electron, that electron that I just placed there, we recall that these electrons are negatively charged. So again, we might start thinking, well, don't they repel each other? Don't they not want to be in the same physical region of space? And certainly that's true to an extent. They are repelling each other. But like in all science, forces really operate in a way that balance each other. So what you really want to do is you want to think of a balance of forces here. So in other words, is it better to couple that electron there down in the ground state with its partner that is maybe causing some repulsion? Or is it better to move it somewhere else? And maybe that's a better option. And we can answer this question by thinking about the fact that the difference in energy here between my 1s and my 2s orbital is relatively large. That's a big difference in energy. I have to supply a lot of energy to excite my electron up to that state. And so to hold my system in this state requires that I put in that much energy. In other words, this is a relatively high energy state. And if I instead drop that second electron back down to where it was, even though, specifically from an electronic perspective, those electrons are maybe less stable than they would be if they were by themselves. So there is a bit of repulsion going there. It's a balance, and this is certainly a better option than having that second electron up into the higher energy orbital. And so this brings us to, I guess, what I might call the final rule, if I'm going to be thinking about how to place electrons into this diagram so that I can build a mental picture of where they are in space and how they're distributed. This makes up essentially what's called the Aufbau principle. And what this principle is all about is we place electrons into this diagram always from low energy orbitals to high energy orbitals. In other words, the first orbital that I'm going to populate is always the ground state, the 1s. The next is the 2s, and it's because of this stratification that we talked about last lecture. The 2p set of orbitals is actually higher in energy than the 2s. Slightly, but in a significant way. So we would populate the 2s next, then the 2p, then the 3s, then the 3p, and potentially the 3d after that, although I will caution you on this one because let's not forget that we're missing some orbitals up here as well. Recall that I ignored the n equals 4 set of orbitals just for a bit of simplicity. So this is called the filling up principle. You essentially just put electrons into this diagram all the way up. And what this, the integration of this Aufbau principle with actually putting electrons into this diagram means that we are coming up with something called an electron configuration. And that's really the point of today's lecture. We want to talk about an electron configuration. So what is an electron configuration? What is an electron configuration? In other words, what do I mean by that? Well, what I mean by an electron configuration is a notation that indicates where electrons are. Now, we have a diagram on our screen right now where we can actually see where electrons are, but we could also use notation. For example, in this diagram, I've got a 1s orbital, and so I can write that down. I've got a 1s orbital, and there happens to be, in the current form of the diagram, 2 electrons in that 1s orbital. And so I can indicate this with an exponent of 2 above my 1s, and I would literally call this my electron configuration. So the diagram that I've got on the screen right now has an electron configuration of 1s2. That's how I would phrase that. And now, why is that even a thing? Why do I care about writing this stuff down? Well, as we'll see over and over again in the future of this class, understanding where our electrons are in terms of their orbitals and then in terms of the size of these orbitals and thinking about how these electrons pair all throughout this diagram will actually definitively give us concrete information to be able to predict properties of elements. We'll be able to understand why certain atoms bond to their neighbors. We'll be able to understand why certain bonds are strong, why some molecules interact with other molecules while others don't. All of this, I promise, fundamentally comes from this notion of where are my electrons in the scope of orbitals that it has available to it. Now, even though I said before that I'm certainly free to take one of my electrons here and say promote it and put it up into some higher energy place, now my electron configuration is no longer correct, so let's get rid of that. While I'm free to do this, most often, and in almost 100% of cases in this class, the only electron configuration that is really worth talking about in any appreciable way is the ground state electron configuration. Now, the ground state electron configuration is defined as the most stable way that we can spread electrons throughout this diagram. And we've already talked about the fact that it is better, it's a better trade-off of forces to leave that second electron down inside the 1s. And so when I talk about electron configurations, unless I say otherwise, I'm really talking about the ground state electron configuration, which again in this case is a 1s2. Okay, so now what I want to do is I want to progress a little bit, and I'm going to show you a bit more of a polished version of this diagram that comes from a textbook. And let's switch our view now to something that's a lot more pretty, if you will. Now I'm going to use this image in a couple of different contexts, but I want you to know that it's exactly the same image as we've had on the previous slide. There's a couple of slight additions though, so let's remember that the 4s and the 4p set of orbitals were not on the diagram that I had just had before. Remember, I left that 4 set off. Now you might also notice that there's a bit of oddness here where the 4 seems to be interstitial between the 3p and the 3d. We'll talk about that in a moment. But the only other real significant edit here to this diagram is that all of my orbitals are indicated as boxes. So sometimes we might call this an orbital box diagram as opposed to what we had on the previous page, which were just lines. That's in some ways just me being lazy and just indicating the different energy states that way, or the different orbitals that way. But we can indicate them as boxes if we like, and likewise, just as we did before, if I have a 1s2 configuration, for example, I can put my 2 arrows in there. Now those aren't very good looking arrows, so let me just adjust my pen here and try it this way. There, that looks a little bit better. So I can do that same thing as I did before, and I would certainly consider this to be a 1s2 configuration. Okay, so in terms of electron configurations, if I have 2 electrons, this is the most stable configuration for 2 electrons, and that's going to be important. So let's give it some practice. Now, one thing I haven't explicitly discussed is this notion of my 4s and my 4p being up here. First of all, let's just look at the s orbitals. So I've got my 1s, my 2s, my 3s, my 4s, and that follows exactly the normal pattern that we would expect. And then if we look, we would notice that we've got our set of p's that come after the s, if you will. And as I go, there are no p's, of course, in the 1, but I add a set of p's for the 2, and then, of course, I'd have a set of p's for all of the other n states or n levels. And so that even looks okay. The trick, though, is with the d's here. And really the answer, like why are the d's interstitial, I guess, between the 4s and the 4p. The answer there has to do with that stratification I talked about a couple of lectures ago. The notion that as I put multiple electrons in all of these orbitals, what happens is that the spacing between these sets, these angular momentum sets, right, the spacing between the s's and the p's, and likewise the spacing between the p's and the d's within a same shell, so the same principal quantum number n, 3 in this case, that spacing gets bigger. Okay, so the more electrons I add, the more spacing is present between all of these different angular momenta in the orbitals. And so what happens is the d and the p here get so far apart that the d eventually overtakes the s. Or you could actually think of this the other way around. The s actually gets lower away from the p, and eventually as the 4s gets lower and the 3d gets higher, eventually they cross paths. So there's nothing fundamentally different going on here than anything I've explained to you already. We already knew that, the s goes down quicker than the p, which goes down quicker than the d, causing a bigger separation happening between all of these sets. And I suppose had we really thought about it a couple of lectures ago, we would have probably expected something like this to happen sooner or later, because we know that as we go from the 1 shell to the 2 shell to the 3 to the 4, these ones are getting closer together anyway. So as I stratify a particular n set, sooner or later they're going to overtake one of the n sets that is, ostensibly above it, or at least should have been above it. So this effect is really just an effect of that same principle I talked about earlier. Now, if we want to go into a little bit more detail about why that actually is, it's not It's not all that strange, or it's not all that complicated. Essentially, let's remember that this is an energy diagram. Don't forget that we're talking about energy here, and we're talking about the energy of electronic states. We're talking about the energy of how electrons can be distributed around a nucleus. And if we add more protons to a nucleus, remember the nucleus has as many protons as is Z, then what we were doing is we're making it more attractive for electrons to be near that nucleus, aren't we? Isn't it better? Aren't electrons more drawn to a larger positive charge at the nucleus? Of course they are. So what that means is that the energy of this 1s orbital, right? In other words, the measure of stability of it, right? How stable is this 1s orbital? And of course, stability, it means low energy. The stability of this 1s orbital must increase as my number of protons goes up. In other words, the 1s orbital must get lower and lower and lower in energy, because any electron in it that is right next to a large positive charge in a nucleus must be very, very happy, energetically speaking. So my 1s orbital will get lower in energy as a result. Now, so will my 2s orbital. My 2s orbital will get lowered in energy for exactly the same reason. But here's the trick. The trick is that the 2s orbital is bigger, isn't it? We already discussed that. The 2s orbital is bigger. Therefore, as I dial up the nuclear charge in the nucleus here, the 2s orbital, while affected, and while it loves that, and while those electrons are happy to see those additional protons, it is not as impacted quite as much as the 1s. The 1s is the one that's much more tightly woven around the nucleus. So the 1s gets lower in energy, the 2s gets lower in energy, but not by as much. Likewise with the 3s. The 3s gets lower in energy, but not by as much. And then if we look at the other angular momenta, the p orbitals, these p orbitals also get lower in energy, of course. So as you add more and more nuclei to the center of this atom, more protons, more positively charged. But any of you who recall what these p orbitals actually look like, let me draw one for you here. Remember, there was a lobe on the top and a lobe on the bottom. Pretend that they were equally sized. I'm not the world's best artist. And we said that there was a node between these two lobes. In other words, there was a 0% chance of finding our electrons there. So imagine this is our nucleus, this little black dot here, and my electron is in a 2p orbital, which means it has equal probability of being up here in this lobe or being down here in this lobe, but a 0% chance of being in the middle. Think about that effect. If I'm dialing up the number of protons in the nucleus, so let's make that nucleus bigger. There we go. So now I've got more protons in the nucleus. In other words, I would draw my electrons closer to me. Of course, my electron here, or potentially my 2 electrons there, would love that. And so the energy of the 2p orbital does go down, no question. But it doesn't go down by quite as much as an s, because look at this giant exclusion zone here. My electron, while it wants to get close to the nucleus, it has a hard time doing it because the orbital it lives in actually has this restriction that says I'm not allowed to come over to the side to get close to the nucleus. I'm not allowed to do that. The orbital fundamentally restricts the motion of the electron. So while the electron is happy and it can get closer to the nucleus, it can't get as close to the nucleus as it would like because of this restricted zone here, this node. And so while the 2p orbital is of course lowered in energy, it is not lowered in energy by as much as the 2s. Okay, so imagine what will happen there. The 2s gets lower, the 2p gets lower too, but not by as much. And that's, again, the reason for this stratification. And you can keep playing that same game all the way up this diagram, and that's why you get what you get. So the moral of the story here is that we have this stratification, we have this interesting order of the orbitals. Makes perfect sense when we think about the structure of these orbitals, and as I dial up the nuclear charge, I can affect how they're distributed. And really what we need to know is, as I add more and more electrons to this diagram, the energy, or like the position of all of these different orbitals does actually fluctuate, right? And so if I'm talking about, for example, helium, Okay, so the helium atom, which is atomic number 2, if I'm talking about neutral helium, then atomic number 2 must have 2 electrons, and that's precisely what I've got here. So I would say that my electron configuration for helium is a 1s2. Technically, we've already done this. Let's try something a little bit more involved. What if we were going to think about something like, say, carbon? Okay, so carbon has 6 electrons. So I need to place 6 electrons in this diagram. I've already placed 2 according to the Aufbau principle that we've talked about earlier. We fill from the bottom to the top. And so I'll go 2 more. I'll put 1 in the 2s orbital here, as I should. And I can certainly put a second electron in the 2s orbital. Now I've got 4 electrons accounted for. I still have 2 more. So certainly I must go to the 2p orbital now. That's my next choice. And the obvious question here is, does it matter which one I put my electron in? Should I put it here, or here, or here? Or does it matter? Now, energetically speaking, let's not forget that these are equivalent. They're all exactly the same energy. So if they're exactly the same energy, then it should be essentially meaningless. So I could put the electron here, but I could have just as easily placed it here, and that would have been equivalent. Likewise, I could have placed it here, and that would have been equivalent as well. In other words, it doesn't matter because they're all equivalent in energy. But now comes the important part. I'll put it right there on the left because that's the first one. In English, we tend to write our words from left to right, so it's natural for me to put my electron there. It's also natural for me to write the first electron as the one with the arrow up, although that is just as irrelevant at this particular point. We can write that in whatever way we want. The real question is, what do I do with my next one? I've got 1 more electron to place in this diagram, but now I have a dilemma. I would argue I have a dilemma. I could put my second electron here with the first, or I could put my second electron, say, over here in an orbital by itself. Or, I guess if we're sort of listing different options, why couldn't I write it over here and maybe it's a downspin electron? There's all kinds of different options here. Are they equivalent? Are they the same? Generally speaking, this is going to require us to think about 2 additional rules that I haven't explicitly explained yet. In the first case, what we like to do is we prefer what are called high spin states. So high spin states are generally more stable than low spin states. So what does that mean? What does a high spin state mean? Well, let's take a look at our diagram right now. Suppose we were to compare 2 of these options that I've got. Let's compare the blue option to the green option, recalling that we have to add an extra electron to the system to get our total of 6. We've already placed the black one, and now we need to choose, is there a better option between the blue one and the green one? Well, the answer here is, as I've said up here, high spin states are more stable. So what is a high spin state? A high spin state is one where we add up more of a particular type of spin. So if I were to look at the blue option here, notice I've got 2 excess electrons in this diagram, both with spin up. In other words, I have an excess of spin up electrons. This is what I would call the high spin state for this particular system. Contrast that with the green electron. Suppose the green electron was the second one I placed in the set of 2p. Now I've got a spin up and a spin down. I have no excess spin. They are effectively balanced, even though they're not in the same orbital. And so that, the green option, is what I would consider to be my low spin state option. And so my point here is that that is a thing that exists, but it is not a good choice if our task is to do electron configurations, which it is today, and in particular, electron configurations of the lowest energy state for this carbon atom. What is the stable state? Well, how should I expect a carbon atom to be to exist? All right. So the real answer here then is to get rid of my green one to conserve my high spin state. That's the one that's more stable. That's the choice I should make. Now, that still ignores the second extra piece of information that I'd mentioned I'd wanted to talk about. The second piece of information here, other than high spin states being more stable, we would generally rather fill orbitals singly before pairing. Now, these rules are related in some sense, although they have distinct use cases in some respects. Notice that what I've got here so far tends to obey both of these, and that's a good thing. You want your population or your electron configuration that you choose throughout these orbitals to adhere to all of these rules. But generally speaking, we want to fill orbitals singly before pairing. So prior to having gotten to this point, we might have asked ourselves the question, which we hadn't asked yet at that point, should I do this, or bring back the blue one, should I do this? Right? Those are two different options. I can keep my second electron here, or I can put my second electron here. And now again, my high spin states being more stable tends to suggest I might want to choose the blue option here, but it deserves some thought. So which of these do I want to do then? Do I want to put my second electron here, or do I want to put my second electron here? The answer is obvious from both of these points. Our next electron that we place in the diagram after we've started with our first one always goes to a different degenerate orbital, degenerate meaning same energy, so a different degenerate orbital, and it always has the same spin as the first to conserve my high spin state. Okay, so there's the final answer here. And these rules generally, you might have seen those before, you might have seen those in high school, but that's really where they come from. Now, the reason behind it, which I know many of you will be wondering, why is it better to put an electron in this next orbital than to put it paired with that first one? Don't electrons like to pair? Well, of course they do, but what electrons like to do more than pair, because let's not forget, pairing electrons causes repulsion. And I'm not saying there isn't repulsion between these two electrons, even in different orbitals. There certainly is. But if I place those electrons in different orbitals, what that allows them to do is get closer to the nucleus. Each and every one of them can get closer to the nucleus. If you imagine what those p orbitals look like, here's a diagram of what those p orbitals look like. Let's not forget that if I have two of them, say these two, they will exist, of course, essentially on top of each other, and I'll have my py orbital in between my px orbital. So they're going to go along adjacent axes like this. And so long as one electron is in one and the other electron is in the other, they effectively stay out of each other's way and allow each other to get closer to the nucleus. And that's the real key here. So that's what we want to do. This is our electron configuration. Now, can we write it out? Can we write out the electron configuration as we did before? Well, we can see that in this case, I also have 1s2, just like I did in helium. And 1s2 is going to be a pretty common component of these electron configurations because we always start there. Directly after the 1s2 is going to be the 2s orbital. And again, let's note that there are two electrons there. Therefore, there is a 2 that goes here. Now, I also have two p orbitals, and this is indicated with 2p like this, and we indicate degenerate sets together here in this diagram. So there's no need for me to write 2p, 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 or 2px, 2py, 2pz. All the degenerate orbitals get lumped together as what is called 2p. And if I check my diagram, I can see, of course, I have two electrons there. So just like I had two in all the others, I have two there as well. And that is my electron configuration for the carbon atom. And so I think we can see how we can continue to fill this diagram, one electron after another. The element directly after carbon would have another electron here, assuming I'm talking about neutral elements the whole time. And then as I add a fourth electron to this 2p set, I am now forced to pair them. And just like before, all three of these are equivalent, so it doesn't really matter where I put the pairing electron. And I can start there and move from left to right if I will. This is just notational. Now, of course, I'm just walking through different numbers of electrons. These no longer correspond to carbon, so let's get rid of that. But this is how we fill electrons through this diagram. Going on, of course, I would get to the 3s, and then I would get to the 3p, which I treat in exactly the same way as I've treated all the others, and fill singly before pairing, always in high spin states. And now I get to an interesting spot. My next best choice here is 4s. It seems better to go to the 4s right now than to the 3d. But that's okay. We've already learned why our orbitals are spread this way. We can accept the simple fact that the 4s orbital is lower in energy. Therefore, it's more stable to put a next electron, if I have one, there. And subsequently, I can put one more there. And only at that point do I begin to start filling up the set of 3d orbitals. Again, singly before pairing, one at a time, always in my high spin state. So I'm just slowly walking through all of these different electron configurations as I fill this diagram. I'm not actually indicating each and every element as I go, but nonetheless, this is how it works. So those are electron configurations. This is how I write out what the configuration of all the electrons are for a particular atom. We're going to make use of this plenty. In particular, we're going to make use of it in the next class. But we'll start our next class by talking about some maybe interesting trick cases or examples of elements that maybe have to be thought of a little bit more carefully. But that being said, what you're looking at here is pretty much the full story, with the exception of just a few important points that I have to raise. These are electron configurations. These allow you to imagine how electrons are distributed in a chemical system. And yes, all of those orbitals that we've seen and been exposed to in previous lectures simultaneously exist, superimposed on top of one another, right on the same atomic nucleus. And so we can start to build a picture in our minds of how these electrons are distributed and how a particular element might behave if it has, say, I don't know, like we had before, say a high spin state in the Ds. Wouldn't that mean I've got a lot of excess spin? Wouldn't that mean my element here would be magnetic? Yeah, so we've already started to understand how to predict magnetism in elements based on something like an electron configuration. There's lots more where that came from, but let's call it a day. I hope you've enjoyed electron configurations, and I can't wait to take this one step further in the next class. Thanks, everyone.